Okay, good morning, everyone. Sorry about the delay. I've got a few things in my presentation that I wanted to work today, so hopefully I can manage to get that to happen. Last day of the winter school. Sun's up. Okay, today we're going to talk about the sulfur cycle, so water, clouds, and aerosols. And first up, I'm just going to cover a couple of the topics from the questions we got yesterday. And the lapse rate I'm leaving till the end of the lecture because if we run out of time, it's okay not to have gone over it. And it's relatively dense, so I could otherwise spend lots of time talking about it. But I just wanted to quickly point out how that simplistic plot yesterday of showing the temperature profile that just bumped up, cooling the stratosphere, is actually much more complicated. And it's more complicated because we've got different gases doing different things at different wavelengths. And so we can see, so down the bottom here we have a nice unit called wave numbers, which is an inverse wavelength. And it's widely used in the infrared range. And here we've got pressure there and approximate altitude here. And so this is marking the tropopause. This is the stratosphere blowing up because it's a nice log scale. But what we're really seeing is this is cooling and the grays are warming effects. And CO2 in the stratosphere is cooling that whole area there. Ozone cools above about 25 kilometers, but below that is actually warming that area there. But overall, due to CO2 absorption, and because it's colder there and you emit from the temperature that you're at, so that's why CO2 is cooling up there. So it's quite a complicated story about why we're seeing cooling and things, but you can also note that water in the troposphere is actually leading to a cooling as well. There. And then these wavelength bands are warming. So complicated with altitude, what effects we're seeing with altitude and wavelength. On the first day, we touched on the ozone problem and the effects in the success of the Montreal Protocol, and then afterwards people wanted to ask me why in Tasmania do we get sunburn more, and I need to emphasise that the ozone hole is not over Tasmania again, and it is just a phenomena that happens over the Antarctic and spreads out, but we actually do need UV for vitamin D production, and so putting sunblock on in winter can be a bad idea because you can actually become vitamin D deficient. So I didn't want to scare everyone. I wanted to create a balance here. So now you've got, this is the erythema weighted UV. So that's UV wavelengths that your skin absorbs. And if you're just exposing your face and hands, and this is the UV indexes. So in summer, we're up in this range, 12 through 15. But in winter, I think you can check on the bottom site today, it's about 5, it's going to be maximum. So you can see that you need to spend, if you expose your entire body, you need to spend about 2.5 minutes out there. And you will get enough UV to create your vitamin D. But most of us don't do that, and we only expose perhaps our face and our hands, and then we really need to spend a reasonable length of time outside, right? So face and hands, we have UV index 5, and so we need to spend about 20 minutes outside in winter to create enough vitamin D. Anyway, it's a bit of a fun fact. So on Monday, I believe, yeah. the vitamin D, yeah. I hope that everyone participates. I just wanted to emphasize also actually what's happened to the UV in the Southern Hemisphere. So we've got the ozone hole, and it's created an increase in, so in a percent change perhaps here, like, so we're here, it's about 5% at our latitudes, but further south higher, so about 8% there. But what you can see here is that clouds and aerosols have actually increased in the Southern Hemisphere. And so the net change, the combined one, is much lower than that. And so the effects of clouds and aerosols is really important for the amount of UV we receive at the surface. And those have changed in the last 30 years, to 2008. Number of effects, but anthropogenic SO2 has been a large one. And then changes in, so there's a lot going on. You've got increased water, and as we're getting through, so there's lots of things go into clouds and aerosols, and I'm really only touch on them a little bit today, but this is also to emphasize their importance. So we've got, we know, so these are our greenhouse gases. So this is from the IPCC. This is a radiative forcing. So this is how much we should care about all these different factors. And we've got carbon dioxide, okay, large positive radiative forcing. The other greenhouse gases, we've got stratospheric ozone causing a cooling here at the moment, and the tropospheric ozone, which is only 10% of the ozone column, is in the troposphere. But you can see its radiative effect is huge. And so our activities that increase ozone at the surface, so driving cars, NOx production, etc., and you've got volatile organic carbon reactions that increase ozone at the surface, really important for accounting for this tropospheric ozone. And so this is radiative forcing with climate between, so how we're changing the climate. So we've changed the tropospheric amount. We've changed the stratospheric amount a bit, but the radiative forcing due to that is not. It's a small cooling here, but a large warming. So we've got stratospheric water vapor from methane that actually warms. It's warmed, created a positive radiative forcing at the surface. So its effect, even though it's in the stratosphere, its effect at the surface, what's it doing? Surface albedo, so land use changes have created a negative radiative forcing here. Contrails. This is generally put in here because everyone's heard of chemtrails, haven't they? They are the fact that how humans are changing the atmosphere, and we can always see these contrails, but a lot of people call them chemtrails, which is, you should Google it, it's conspiracy theory. So aerosol radiation interactions and aerosol cloud interactions. These are the two largest negative radiative forcings, and you can appreciate, so we've got quite a large error bar here on the CO2, but that's about double in terms of what is our understanding here of these effects. And so the total anthropogenic, of course, is a positive radiative forcing of about 2.2 watts per square meter. So this is why we care about clouds and aerosols. The radiative forcing, it will be, I guess it would be top of the atmosphere. No, the top should be at the surface radiative forcing. Peter can correct me because the top of the atmosphere doesn't make any sense. It must be at the surface, right? Yeah. So the sulfur cycle, it's natural and anthropogenic. We've got the influence of on the hydrological cycle. We've got clouds, aerosols, and climate impacts due to sulfur. There's the health effects of sulfur, and we're going to touch on geoengineering the climate using sulfur, and that's called radiation management, solar radiation management. So this is a cycle, a sulfur cycle for the atmosphere. So we've got a number of sources that pump sulfur into our atmosphere. So volcanoes, grass and forest fires, so any biomass burning. We've got fossil fuel burning will release sulfur, and different fuel types are more or less sulfur rich. So China's coal is particularly sulfur rich, and some of their major air quality problems derive from that. In comparison, Australian coal has less sulfur in it, but and the US coal has a lot. In saying that, there are sulfur scrubbers on the coal power plants in the US, which have largely brought that down, and that's not the case in Australia. Shipping, a large source of sulfur low down. And then we've got algae and DMS, so dimethyl sulfite. So algal blooms produce this, and it's deemed to have a climatic effect. We can get deep convection, bringing these sulfur products into the stratosphere, or we can have large sulfuric injections from volcanoes. And that's relevant later. And then there's a large sulfur layer in the stratosphere, the sulfate aerosol in the stratosphere, and I'll show you that in a moment. So this is just, again, a summary of all those different sulfate sources, anthropogenic, natural, and then we've got the health effects of sulfur. So it's sulfur dioxide quickly forms an acid, sulfuric acid, very strong acid, and it's a great irritant, causes all sorts of lung health problems, so respiratory, cardiac arrest as well, and so chronic bronchitis, etc. It also increases the acidity of rain, so acid rain from sulfur. And the atmosphere, of course, has no boundaries. Acid rain in Europe can be produced from chemicals in neighbouring countries. So you can worry, your air pollution in your own country can be controlled by what's coming in from other sources, other countries. And now, natural rain should have a pH of about 5. And so if you put this in the atmosphere, you make things much more acidic, and you get acid rain. And so if you're in a remote region, it's about here. But during the fog in Los Angeles, for example, you can have a pH of around under 2. And that's, it's more acidic than lemon juice. It's not quite at battery acid level, thank goodness. Vinegar's here. And this is where you've got cloud water over New York. We can change the acidity of the rain, and that has effects on cropping. So this is acid rain produced from, it's predominantly a Northern Hemispheric phenomenon, because there's a lot more sulfur emissions in these regions, but you can see we've got China, Europe, and the east coast of the US here, widely affected by the amount of sulfur being emitted in these regions. So I'm going to touch briefly on Lovelock. Now, Lovelock also was one of the first people to measure CFCs in the atmosphere. So he's one of these people who doesn't like staying in one field and likes to do all sorts of things. And he came up with the Gaia theory that organisms co-evolve with their environment, and it's a self-healing earth. So, for example, global warming is going to increase temperatures, which will increase ocean biology, that will increase dimethyl sulfur produced by the ocean. Clouds will form, and that will cool down the surface. So it's a self-healing earth. It's been largely discounted, but it's an interesting theory of a negative feedback. Now I'm going to show you what volcanoes do. And if I can get both on the screen. And bushfires in particular over doesn't look good. It looks lovely on my screen. I'll just share my screen so you can have it too. I think. Okay, it's arrangement I haven't mirror. Great. Thanks. Okay, so this is aerosol in the stratosphere from satellite measurements, and what you can see that we're about halfway through. We'll start here. So this is the general background, and because these are satellite measurements, you're only covering the light part of the Earth at one time. So it will move between the north and there's part of the planet that's not covered. But what's quite nice is when you so we have small volcanoes going off in the northern hemisphere up here, and so that'll inject. You start to see the circulation of the stratosphere. So a volcano in the northern hemisphere will increase the aerosol loading there. And the date, oh yeah, so that was the bushfires in Melbourne, so Black Saturday fires. So you saw that red go round, circulate, and eventually come out. Large volcanoes now in the northern hemisphere, and you see it's really difficult for it to cross the tropics, and it doesn't really. So it just gives you an appreciation of, one, how quickly it will spread out and blanket the Earth, and that's really important for some geoengineering arguments. So that's the Junge layer, and it's actually mainly carbonyl sulfide, which we heard Peter talk about yesterday, in the stratosphere, and forming a sulfur exists as that, but also forms the sulfate aerosols in the stratosphere. And volcanoes have done this a lot, and the reason why this is interesting is that it actually cools the surface of the planet by a significant amount. And so Pinatubo, for example, injected 6 to 11 teragrams of sulfur into the stratosphere, and that resulted in a 0.5 Kelvin global temperature increase. You see that pulse there. Now, there have been other volcanoes, so Agung, El Chichong, and so Agung was 63, El Chichong 81, 83. And Pinatubo was 92. And the varying amounts and varying cooling following that. Yes, Pinatubo was in the tropics. So it did go both ways. Yeah. So big ones in the tropics, and they do spread into both hemispheres. Otherwise, it can be relatively confined. So if you want to just target, and I'll come to this, so geoengineering has been proposed for solar radiation management. So we can effectively use that. So aerosols reflect the solar radiation back to space. You're not getting that heating input coming back in. So you're increasing your albedo by doing this. And so it's a widely proposed, I guess, way of cooling the surface if we don't manage to do so through mitigation of greenhouse gases. But as you can imagine, there are a couple of opponents to it. And so geoengineering is like a junkie figuring out new ways of stealing from his children. And how can you engineer a system whose behavior you don't understand? Are a couple of the statements that go along with this. And but if we just stick to the science, like how viable is it? Are we able to do this? And in terms of geoengineering proposals, this is one of the more effective, and it's reasonably cheap. So you can put up a tower into the stratosphere. That's 10 kilometres. That's fairly insane. You can fly up there. You can launch these balloons. People have calculated the amount of rubbish you would accumulate quickly if you were to get sulfur to come in that way, or you could have cannons going up. Flying and injecting SO2 directly is one of the fastest, the most economical, actually. And it is very economical. It actually accounts for only 0.3% of Australia's GDP to do this. One person could do this if they decided to. Small island states could, for example, do this. And that becomes somewhat frightening because there is no international agreement there, except you cannot, as an act of warfare, change another country's climate. That is the only international policy instrument at the moment that could stop this happening. So we'll carry on in the thought experiment that we go ahead. So, you know, we can do 9 flights a day, nine aircrafts with 3 flights a day. You've got a setup cost of this, but you can see your running cost is not huge. And these are, okay, so these are, yeah, in terms of dollars. So, you know, $225 million. That's not much to see in the grand scheme of things. It's cheaper than mitigating, that's for sure. But they do not. So I'll move to aerosols. There are a lot of risks involved, and so by increasing that albedo and stopping that short wave coming through does not stop acidification of the ocean. It does not stop the commitment to a temperature rise if you were to suddenly clean up the stratosphere. And we don't know that the aerosol formation processes well enough, and we cannot model them well enough yet to actually know how this might work if you continue to do it. Because once you started doing it, you couldn't stop. But if, for example, we were going to see catastrophic massive ice loss, which would see like 20 or 30 meters of sea level rise because of the temperature we've already committed to, in conjunction with aggressive mitigation strategies for greenhouse gases, this could stop us going over a detrimental temperature threshold. It would, yes. There's very many arguments that we don't know the system well enough to know what might be the side effects of doing it. Yeah. Right. And so, yeah, what times of year, all sorts of things like that. And it's definitely not balanced because you create droughts in Asia and Africa due to doing this. And that they've seen that after the volcanoes, those have been areas which have had droughts. So there would be a lot of opposition to doing so. But a lot of people are talking about it. So this brings us to aerosols. We now know why we should be interested, and their roles are different. But in the troposphere, an aerosol is a condensation of small droplets, and it can be. So it's just a collection of material, really. So they can actually be dry, relatively dry or hydrophobic aerosols. And I'm going to mainly talk about the aerosols which go on to initiate and form clouds. And we'll just deal with water first of all. So water can come together with chance collections in the atmosphere, and that process is called homogeneous nucleation. That means that there's no aerosols, there's no little particles or seeds to help that along. And you need to overcome, so you can imagine if your volume is really small, your surface area is extremely large. You need to overcome a surface tension. And so it's easier for a larger particle to form, a larger droplet to form than a smaller one. And if you've got this collection of a few water molecules, the chance of re-evaporation is large because you haven't overcome the energy to actually grow. And that energy you need to change from a gas to a liquid phase, that's called latent heat. And so the latent heat release is important in the atmosphere. So droplet formation, it requires the condensation. So that means condensation means you go from gas to liquid. You require that, you need work to do that, and so you need to overcome that surface temperature. And that's proportional to the area of the droplet. Yeah. And the source of energy is that latent heat. So here, so it's proportional to the temperature and the degree of saturation of the air, so your relative humidity. So you're not going to get fog if the temperature is really warm and your humidity is very low. But this morning, temperature is very low, the humidity is relatively high. We've had a lot of rain, and so likely to get fog and condensation happening. So if we continue this more, now this here is a relatively complicated way of saying relative humidity. So it's the water pressure in air over the saturation pressure. And then we've got temperature and the radius of your droplet. So we need to overcome, and that's our latent heat there. Now, if the latent heat is less than the surface tension, you don't get droplets. When it's greater, you do get droplets. You need to have the humidity of air greater than the saturation. So relative humidity needs to be greater than 100%. In clouds, relative humidity is greater than 100%. That's all that's saying there. At small radii, it's much, and the volume is much smaller than the radius. And so your latent heat is low, and you're unlikely to get your droplet forming. So there's a critical radius at which the latent heat equals the surface tension. And you need to be over that critical radius for your droplet to kick off and to form. And what you can see is as you move up, so these are supersaturations of 1%, of 12%, and so you can see that those critical radii get much smaller. So this is a huge droplet actually at 1 micron, and generally you're getting, this is like 10 nanometers. And so talk about like 3 nanometers about the formation size of the droplet. So in the real world, molecular collisions, so water just coming together, will only form droplets much, much smaller than this. And it requires enormous amounts of supersaturation to grow. And then that's above 300. So relative humidities of 300%. They just don't exist in the atmosphere. And so that's not found in nature. So while you might have a lot of water in the atmosphere, unless you have aerosol particles, you're not going to get growth of droplets for rain, for clouds. And that's where we get aerosols and cloud condensation nuclei coming in. So aerosols are suspensions, the liquid or solid particles in the air. And so you need something else apart from water. And that's where sulfuric acid is extremely good, because it overcomes those barriers to formation and quickly, and you can kick it off. And they also, so CC, and I'll come to in a moment, there are many sources. They're biological, so seeds, pollens, bacteria, salts. You've got dust here, and then fuel combustion. All of these things put things in the air which can act as a seed for your aerosol formation. And as we know, they can be largely associated with allergies and pollution. And the cloud condensation nuclei are a subset of these aerosols. So it's sort of a continuum. You're getting water, then through aerosols, and then into clouds. But only a few of them will go into that cloud condensation nuclei part, where they start to take up large amounts of water. And then they will go on to form big clouds and things. So this is another way of saying that. So you've got those ultrafine, these are these particles forming all the time, and they're growing. So you've got growth, and growth by condensation. So they start to take up water. At some point, they become climatically relevant. Not that these aren't relevant, but here they take on clouds. They start becoming clouds. So these can effectively reflect the radiation, but clouds, as you know, are really effective at doing that. So that goes on, and you form clouds reflecting radiation, and you've got a background aerosol amount there. And the sources here, you've got urban sources and biological sources for your aerosols. This is volatile organic carbons. So that is many of your, like trees will produce that. Isoprene, for example, is one of those compounds. And then we've got polycyclic organic aromatics compounds. So that's largely from your fossil fuel sector. So we've got a large range of particles, and so air chemistry spans that entire range. You've got optical issues there, clouds, precipitation, and so these are different aerosol groupings there, and climate models start to group them in these. So you've got the Aitken mode, which is really your formation, and you've got your larger particles and then really giant ones. And of course, raindrops is an example of once you're out and you're getting into millimeter size droplets. I'm going to come to the particulate matter less than 2.5 microns, because this is, you may or may not have heard about it, but it's the size of an aerosol which you can breathe really deeply into the far reaches of your lungs, and they're extremely bad for you to do that. So you can fit here, you could fit a number of them across a human hair. So it's a human hair here, and you get a lot across. Now you've got other compounds which are also in that range, so metals, organic compounds come into that, dust, pollen, mold, etc., they can be in that range. And for comparison, that's what a sand granule is there. So the health effects of PM 2.5. We can have so premature death due to respiratory and cardiovascular disease due to exposure. So there's estimated, at least here in Australia, and this number may be outdated, so 1,590 deaths each year attributable to the fine particle pollution. Now, it's obviously very difficult to, because it acts as an aggravator. So above background conditions of aerosol. And you get a lot of hospital emissions each year. It is now a Class 1 carcinogen. It's classified by the World Health Organization as a Class 1 carcinogen. And then that puts it in the same category as asbestos, tobacco smoke, diesel exhaust, and of course there it is there. So and at the moment there is no control in Australia on PM 2.5. So there is no threshold, and there is we do need to monitor it now. But it causes visibility reduction, and of course it, as I pointed out, it influences how clouds form. And it influences the precipitation. If you've got a lot of small aerosol within a cloud, it will actually suppress precipitation and make the clouds last longer. So it actually perturbs clouds. And that's what aerosols do, and this is how aerosols and climate interact. So we can have the direct effects, and that's through scattering, but they can also absorb, and so that's what we see in the stratosphere as well. You can get a local heating, you get a cooling below it. So this is what would happen with the geoengineering scenario, for sure, but it happens in cities as well. It happens everywhere you've got aerosols. You can get this, so you get atmospheric circulation and mixing processes, and you spread the cooling regionally and in the vertical. So that's the cooling there. And then you can have the warming, so this is absorbing and cooling effects there. Now they can interact with clouds and change the properties of clouds, and that's what they're doing here. So you can, if you insert a lot of little aerosol particles into your cloud, you can create this. So they serve as, so they create clouds, but they change the properties of clouds that are already there. So we can get, what happens is you get several smaller droplets, and a smaller droplet is more reflective. So you increase the reflectivity of the cloud, you suppress the precipitation, and you make the cloud last longer, because if your cloud is not precipitating, it doesn't dissipate. You're not getting rid of the water, so it'll last longer. So those are all the complicated, those feedbacks that we hear about aerosol cloud interactions and indirect effects. These are called the indirect effects of aerosols. So now we get into clouds. Now, climate change is going to change clouds and has done so a little bit. So we're going to get, we're putting more water in our atmosphere as well, so the potential to form clouds goes up. So in the tropics, we're going to get increased heights of our high clouds. We're going to get broadening of this Hadley cell through the circulation. Again, we're getting higher clouds, and we saw that the tropopause was moving up. We're getting a poleward shift of the storms, so there's storm tracks over the Southern Ocean moving southward, and that having influence. We have more polar clouds, so more low-level clouds over the polar region that actually will cool that surface there somewhat. And what we do get over the tropics, and so is less low clouds. we're raising that melting level, so we're increasing the temperature of the entire troposphere. And so the level at which you get the melting, which means the level at which you're getting rain and everything forming, is increasing. So that's all the effects of climate change on precipitation and clouds. I am going to put all of these lectures up on the web, so if you want to capture that later. So we dealt with homogeneous nucleation before. Now, heterogeneous nucleation just means you've got an aerosol particle and you're forming your droplets through having some sort of seed there. Have everyone heard of cloud seeding? So it's on purpose going and trying in an area which it seems to be, there's enough humidity, etc., but there's just too clean, we don't have enough particles or ways of forming the clouds, so you can go up there and you put sea salt into the atmosphere, for example, and create clouds. And there are these interesting wind machines that do that, creating low-level clouds. Another nice geoengineering scenario. So we're getting the condensation of water in supersaturated conditions on some object, which is your cloud condensation nuclei. We need to, so we need the minimum droplet size at a 1% supersaturation is 0.1 microns. So that just record. So a 1% supersaturation can condense onto small insoluble particles at about that level. So you've got this insoluble center, but you're getting condensation on the outside. Quite interesting. And they're abundant in the atmosphere. There's a lot of sources that can do that. And so you've got, and these are all at 1% supersaturation. So you've got different concentrations of these cloud condensation nuclei. And so you can see that in the Arctic air, that's really low. But over continental regions, that's extremely high. So your potential for forming clouds, as soon as you get a supersaturation over continental regions, is relatively high. And that's some of the drivers behind tropical, thunderstorms in the afternoon, etc. You've got a lot of heating on the surface, putting a lot more water in the atmosphere, and you've already got the potential to form clouds all the time over these regions. So as soon as you add water to the system, you get clouds forming. And so we've got different CCN over different areas. And so over the marine areas, these are sort of the distribution of your cloud condensation nuclei. So that's the droplet concentrations there. So that's marine and marine. And then you've got the different continentals. So you've got marine clouds, you've got fewer but larger droplets. They're much more likely to rain. But over the continental regions, you've got numerous smaller droplets, and those are less likely to rain. So they're going to live longer, those clouds, than the marine clouds. So we've got the different types of clouds there. You've got liquid water here below that melting level. Then you're getting ice above that. And you're getting super cooled and then glaciated ice up there. And so you need nice deep clouds to form the snow that we saw yesterday. Or you just need this melting level to be quite low, which is also the case. Yeah. So different types of clouds. Some nice pictures. See how far I am. So warm clouds are where the temperature is above zero everywhere. You're going to have liquid precipitation there. It's made up by small drops only, usually, and then they grow through condensation, which is or collision. So in clouds, you also start to get large updrafts and downdrafts, and so they're all getting mashed together, and so they start to conglomerate. So that's growth by condensation, and that happens. So it's happening all the time. And how quickly things will fall is given by their terminal velocity. Now, you've got drag, frictional drag as well. influencing that. So all those effects come into calculating precipitation rates. So larger drops have larger terminal velocities. Smaller drops don't fall as fast because it's harder for them to overcome the gravitational, the drag. The gravity force, of course, is the same, but it's the frictional forces that is harder to overcome to get different terminal velocities. And so we've dealt with condensation growth. They can also grow through collision, and rain relies on both of those processes. And it changes over time. So as the clouds age, you've had more collisions. You've had more time for the collisions to happen. So older clouds will have larger droplets. And so older clouds will precipitate. To start with, fresh clouds, you can guarantee it's not going to precipitate. But quickly, and so how much mixing you're getting within the cloud will determine how quickly you will start the precipitation processes. Now, I think this starts to, I'm pretty much finished. If you would like me to go into touch on how the lapse rate of the atmosphere goes on, or I can just talk to the person who asked me the question yesterday. Otherwise, I can take questions now. It's very dynamic. It will re-evaporate if you get an air mass come in that's really dry, then it will immediately re-evaporate. And the same, often through ice and things falling, it will evaporate before it hits the ground. Mm. Well, it's just the polar regions that they have a problem, right? So the circulation in the stratosphere. And in all seriousness, it's the amount of sulfur you need to introduce to the stratosphere is very small, which is why it's relatively cheap. And people have calculated you get a little bit of transfer from the stratosphere into the upper troposphere, and where you might form cirrus clouds and etc. But the effects on acid rain etc. are minimal compared to what we are doing at the surface for sulfur. Yes. Right, so we saw that aerosols will heat up when they absorb, just like ozone, and it is a shortwave radiation. So all you're doing is increasing the reflectivity of the planet. So you're increasing the Earth's albedo, and so you're trying to reflect out that short radiation so it doesn't reach the surface and start going into the emission of the surface part of the problem. No, so it's purely reflective. So you just it starts to act like a mirror. So or you've got water around, you've got something in the middle, and you're getting reflection straight out of the UV radiation. So it's opaque in that region. It does absorb, and they do absorb, like ozone, which is then an electronic transition and blows the particle apart, the atoms, the molecules apart. But aerosols are bigger, and we're not talking about really molecular transitions anymore. It's just a pure, like putting some of the other geoengineering proposals are like putting space mirrors in the way, all sorts of crazy ideas. It's once it's formed an aerosol. Yeah. Yeah. So the idea of putting the sulfur dioxide in the stratosphere, it's not the sulfur dioxide that's doing it, it's the fact that sulfur dioxide quickly forms aerosols. And cool. Sorry? Yeah, yeah. So certainly over the marine environment, they can be quite limiting because it's very clean air, and there's a nice Soren has a really nice video in the Arctic